The Large Hadron Collider, LHC, is the world's largest and most powerful particle accelerator. It first started up on 10 September 2008 and remains the latest addition to CERN's accelerator complex. The LHC consists of a 27-kilometer ring of superconducting magnets with a number of accelerating structures to boost the energy of the particles along the way. Inside the accelerator, two high-energy particle beams travel at close to the speed of light before they are made to collide. The beams travel in opposite directions in separate beam pipes, two tubes kept at ultra-high vacuum. They are guided around the accelerator ring by a strong magnetic field maintained by superconducting electromagnets. The electromagnets are built from coils of special electric cable that operates in a superconducting state, efficiently conducting electricity without resistance or loss of energy. This requires chilling the magnets to minus 271.3 degrees Celsius, a temperature colder than outer space. For this reason, much of the accelerator is connected to a distribution system of liquid helium, which cools the magnets, as well as to other supply services. Thousands of magnets of different varieties and sizes are used to direct the beams around the accelerator. These include 1232 dipole magnets, 15 meters in length which bend the beams, and 392 quadrupole magnets, each 5 to 7 meters long, which focus the beams. Just prior to collision, another type of magnet is used to squeeze the particles closer together to increase the chances of collisions. The particles are so tiny that the task of making them collide is akin to firing two needles 10 kilometers apart with such precision that they meet halfway. All the controls for the accelerator, its services, and technical infrastructure are housed under one roof at the CERN Control Center. From here, the beams inside the LHC are made to collide at 4 locations around the accelerator ring, corresponding to the positions of 4 particle detectors: ATLAS, CMS, LS, and LHC. The safety of the LHC. The Large Hadron Collider, LHC, can achieve an energy that no other particle accelerators have reached before, but nature routinely produces higher energies in cosmic ray collisions. Concerns about the safety of whatever may be created in such high-energy particle collisions have been addressed for many years. In the light of new experimental data and theoretical understanding, the LHC Safety Assessment Group, LSAG, has updated a review of the analysis made in 2003 by the LHC Safety Study Group, a group of independent scientists. LSAG reaffirms and extends the conclusions of the 2003 report that LHC collisions present no danger and that there are no reasons for concern. Whatever the LHC will do, nature has already done many times over during the lifetime of the Earth and other astronomical bodies. The LSAG report has been reviewed and endorsed by CERN's Scientific Policy Committee, a group of external scientists that advises CERN's governing body, its council. The following summarizes the main arguments given in the LSAG report. Anyone interested in more details is encouraged to consult it directly, and the technical scientific papers to which it refers. Cosmic rays. The LHC, like other particle accelerators, recreates the natural phenomena of cosmic rays under controlled laboratory conditions, enabling them to be studied in more detail. Cosmic rays are particles produced in outer space, some of which are accelerated to energies far exceeding those of the LHC. The energy and the rate at which they reach the Earth's atmosphere have been measured in experiments for some 70 years. Over the past billions of years, nature has already generated on Earth as many collisions as about 1 million LHC experiments, and the planet still exists. Astronomers observe an enormous number of larger astronomical bodies throughout the universe, all of which are also struck by cosmic rays. The universe as a whole conducts more than 10 million LHC-like experiments per second. The possibility of any dangerous consequences contradicts what astronomers see. Stars and galaxies still exist. Microscopic black holes. Nature forms black holes when certain stars, much larger than our Sun, collapse on themselves at the end of their lives. They concentrate a very large amount of matter in a very small space. Speculations about microscopic black holes at the LHC refer to particles produced in the collisions of pairs of protons, each of which has an energy comparable to that of a mosquito in flight. Astronomical black holes are much heavier than anything that could be produced at the LHC. According to the well-established properties of gravity, described by Einstein's relativity, it is impossible for microscopic black holes to be produced at the LHC. There are, however, some speculative theories that predict the production of such particles at the LHC. All these theories predict that these particles would disintegrate immediately. Black holes, therefore, would have no time to start accreting matter and to cause macroscopic effects. Although theory predicts that microscopic black holes decay rapidly, even hypothetical stable black holes can be shown to be harmless by studying the consequences of their production by cosmic rays. Whilst collisions at the LHC differ from cosmic ray collisions with astronomical bodies like the Earth in that new particles produced in LHC collisions tend to move more slowly than those produced by cosmic rays, one can still demonstrate their safety. The specific reasons for this depend whether the black holes are electrically charged or neutral. Many stable black holes would be expected to be electrically charged, since they are created by charged particles. In this case, they would interact with ordinary matter and be stopped while traversing the Earth or Sun, whether produced by cosmic rays or the LHC. The fact that the Earth and Sun are still here rules out the possibility that cosmic rays or the LHC could produce dangerous charged microscopic black holes. If stable microscopic black holes had no electric charge, their interactions with the Earth would be very weak. Those produced by cosmic rays would pass harmlessly through the Earth into space, whereas those produced by the LHC could remain on Earth. However, there are much larger and denser astronomical bodies than the Earth in the universe. Black holes produced in cosmic ray collisions with bodies such as neutron stars and white dwarf stars would be brought to rest. The continued existence of such dense bodies, as well as the Earth, rules out the possibility of the LHC producing any dangerous black holes. Strangelets. Strangelet is the term given to a hypothetical microscopic lump of strange matter containing almost equal numbers of particles called up, down, and strange quarks. According to most theoretical work, strangelets should change to ordinary matter within 1,000 millionth of a second. But could strangelets coalesce with ordinary matter and change it to strange matter? This question was first raised before the startup of the relativistic heavy ion collider, RHIC, in 2000 in the United States. A study at the time showed that there was no cause for concern, and RHIC has now run for 8 years, searching for strangelets without detecting any. At times, the LHC will run with beams of heavy nuclei, just as RHIC does. The LHC's beams will have more energy than RHIC, but this makes it even less likely that strangelets could form. It is difficult for strange matter to stick together in the high temperatures produced by such colliders, rather as ice does not form in hot water. In addition, quarks will be more dilute at the LHC than at RHIC, making it more difficult to assemble strange matter. Strangelet production at the LHC is therefore less likely than at RHIC, and experience there has already validated the arguments that strangelets cannot be produced. The analysis of the first LHC data from heavy ion collisions has now confirmed the key ingredients used in the LSAG report to evaluate the upper limit on the production of hypothetical strangelets. For more details, see this addendum to the LSAG report, Implications of LHC Heavy Ion Data for Multi-Strange Baryon Production, 2011. What do you think of our video? Let me know in the comment section below. If you enjoyed this video, make sure to hit that like button. Also subscribe to our channel before you go.